Okay, the goal of this series is to understand how to solve integrals like the following. An integral where you have a difference of squares inside of a square root. Something like this. These ones can be difficult to solve because a difference inside of a square root is somewhat intractable. It's not easy to deal with. So what we want to do is we want to transform that difference into something that interacts more nicely with the square root and ultimately cancels it out. We can do that using a trigonometric substitution. So there's three key identities that we typically use to solve integrals of this form. They're all very closely related, and I'm going to show you where they come from right now. So let me draw a right triangle inside of a unit circle. So a unit circle has a radius of 1. And let me call this side y and this side x. And I'm going to label this angle as theta. And the right angle is here. Okay, so if you remember the definitions of the trigonometric functions, we have cosine of theta is equal to adjacent over hypotenuse. The adjacent side here is x, and the hypotenuse is 1. So that means cosine of theta is equal to x. The definition of sine of theta is opposite over hypotenuse. So sine of theta is going to be equal to y over 1, which is just y. So sine of theta equals y. That means the coordinates of this point are xy, or cosine theta, comma, sine of theta. Okay, so now we're going to discover the first important identity that we're going to need by using the Pythagorean theorem on this triangle. So the Pythagorean theorem says that x squared plus y squared is equal to 1 squared for this triangle. Well, 1 squared is just 1, so x squared plus y squared equals 1. And now we already know that x is equal to cosine of theta from here, and y is equal to sine of theta from here. So we can plug those in, and we're going to get cosine squared of theta plus sine squared of theta is equal to 1. And we can take this identity and rearrange it to get cosine squared of theta is equal to 1 minus sine squared of theta. And this right here is one of the identities we're going to use to solve integrals like the one I showed you above. Because what this does is it takes a difference on this side and it transforms it into just a single thing squared. And that is a very nice thing to have underneath a square root. So there's one of the identities that we're going to need. There's two more, and the other two are essentially the same identity, just rearranged. So let me get that one for you. So if you take this identity, divide everything by cosine squared of theta, both sides by cosine squared of theta, you will get another identity. Cosine squared over cosine squared is just 1. And then sine squared over cosine squared is tangent squared. And if you remember, 1 over cosine is equal to secant of theta. So 1 over cosine squared is secant squared of theta. So this one lets us transform a sum like this into a single thing squared like this. So this is the other identity we're going to need for trig substitution. And the last one is simply rearranging this one. If we subtract the 1 from both sides, we will get secant squared of theta minus 1 is equal to tangent squared of theta. So these are the 3 identities we're going to use to solve integrals like the one up above. So I'll label this one as 1, this one is 2, this one is 3. So let me just tell you what types of integrals they each help you solve. So for example, the first one would let you solve something where you have, say, a square root with a number minus, say, x squared. Something that contains this. The second one would let you solve something where you have a square root with a number, let's say 64, plus a function squared, let's say x squared. And the last one would let you solve an integral that contains your x squared minus some number squared. So in the next video, we will actually start applying these identities to solving integrals.